Hello children, welcome to online classes. Today we will discuss main points from chemical kinetics. Now, it is a branch of chemistry which deals with the study of rates of chemical reactions and the factors which determine their rates. So, it is a branch of chemistry which deals with the study of rates of chemical reactions and the factors which determine their rates. Let us start with the rate of reaction. So, meaning of rate of reaction. Rate of reaction is the change in the molar concentration of one of the reactants and products per unit time. So, rate is the change in the concentration of reactants or products per unit time, and mathematically it is represented as rate is given by plus or minus dc by dt. Plus or minus dc by dt. Here dc stands for the change in the concentration and time dt stands for the time we have, time interval. So dc by dt is the change in the concentration of reactants, dt per unit time we have. And coming towards plus or minus sign. As the time runs, the concentration of reactants gets reduced. Therefore, minus sign is used to express with respect to reactants now. And as the time runs, concentration of the products will be increasing, and therefore plus sign is used to express with respect to products we have. Therefore, finally plus or minus dc by dt is used so that it includes both. Now, for a reaction A plus 2B giving rise to 3C plus 4D, the reaction rates are related as rate is equal to minus dA by dt is equal to minus 1 by 2 dB by dt and plus 1 by 3 dC by dt and plus it is 1 by 4 dd by dt we have. So the minus signs are there with respect to reactants A and then B, and plus signs are coming with respect to products C and then D we have. And coming towards dA by dt, if you take only dA by dt and then dB by dt, these two terms, they are called rate of disappearance of A, rate of disappearance of B. Similarly, if you take dC by dt and then dd by dt, these two terms are called rate of appearance of C and rate of appearance of D we have. So, without dividing with respect to coefficients, you are going to get rate of appearance, rate of disappearance. If you divide with respect to coefficients, we are going to get the rate of reaction. This is regarding meaning of the rate of reaction. Then comes the graphs which are representing the rate of reaction. So as we already seen, plus sign signifies increase in the concentration of the product formed, and minus sign signifies the decrease in the concentration of reactants used. And coming towards units, since it is a change in the concentration per unit time, so concentration units by time will come. Concentration is moles per liter by second. Or as in SI units, it is a mole per meter cube per second we have. If at all you have a gaseous components, then you are going to use atmospheres per second then now. So for aqueous solutions, units are mole per liter per second, and for gaseous components, units are atmospheres per second is used to express the rate of reaction. And if you see the graphs here, now suppose R is giving rise to P, means reactants are giving rise to products for us now. As the time runs here, the concentration of the reactants will be decreasing. Thereby you can see a decrease in the graph coming for reactants now. So this stands for the concentration of reactants now. And as the time runs, the concentration of the products will be increasing, and therefore this graph shows the concentration of the products order we have. So this is a graph representing how the rates of how the concentrations of reactants and products are changing with respect to time. Next one, the factors which are influencing the rate of reaction. First one will be the nature of reacting substances. So ionic reactions are very fast when compared to covalent reactions, because in the case of ionic reactions, only rearrangement of ions are taking place and therefore they are fast. When it comes to covalent reactions, at the time of reaction, the existing bonds have to break and new bonds have to form. It takes certain period of time, therefore covalent reactions are slow. So finally, ionic reactions are fast and covalent reactions are slow. When it comes to temperature, the rate of reaction increases with increase in temperature. This can be dealt in detail in the coming slides now. So remember, rate of reaction is always increasing with increase of temperature, whether it can be endothermic reaction or else it can be even exothermic reaction also. Coming towards concentration of reacting substances. Rate of reaction increases with increase in concentration of reactants. Of course, except we have here zero order reactions are exceptional here. In the case of zero order reaction, rate is completely independent of the concentration. In all other reactions, rate depends upon the concentration. When concentrations are increased, rate is going to be increasing. Then coming towards effect of catalyst. A positive catalyst always increases the rate of reaction, whereas a negative catalyst will be decreasing the rate of reaction. So factors affecting nature of reactants, temperature, concentration of reacting substances, and the catalyst we have. These are the factors affecting the rate of reaction. Then comes law of mass action. Law of mass action, that is at constant temperature, it says that the rate of a chemical reaction is directly proportional to the product of active masses of reactants, each raised to the power equal to its stoichiometric coefficient in balanced chemical equation. It was proposed by Goldberg and Bravais. Once again, the law of mass action states that the rate of a chemical reaction is directly proportional to the product of active masses of reactants, each raised to the power equal to the stoichiometric coefficient in the balanced chemical equation. And here the active mass is nothing but molar concentration, that is moles per liter or as moles per decimeter cube we have. Or if you take gases, it's a partial pressure, nothing but Newton per meter square, or it can be atmospheres we have. So therefore active mass stands for the concentration only, expressed in terms of moles per liter or as in terms of atmospheres we have. This is regarding law of mass action. Let us take up a reaction, say 2A plus 3B giving rise to here say C and 4D we have. Let us write the rate of reaction according to law of mass action. So rate is given by K into A square into B to the power of 3 we have. So here 2 is nothing but coefficient of A here and 3 is a coefficient of B here now. So this is according to law of mass action. Rate is given by K into A to the power of 2 into B to the power of 3 we have. And active mass is a molar concentration only. Active mass means number of moles by volume in decimeter cube we have. This is regarding law of mass action. Then comes the meaning of specific rate. The rate constant or specific reaction rate or velocity constant. Now for a reaction, the rate constant can be defined as rate per unit concentration of reacting substances. Rate per unit concentration of reacting substances we have. Means when, for example, when you take a reaction like say A plus B giving rise to products here now. So rate is equal to K into concentration of A, say into concentration of B we have now. If you take A and B as 1, then K becomes equal to rate only. So therefore K is defined as rate per unit concentrations of these two substances. So rate constant can be defined as rate per unit concentration of reacting substances. K depends on temperature and a catalyst for a given reaction. Means if you increase the temperature, rate will be increasing, thereby rate constant also increases. And if you add a catalyst, rate will be increasing, then also K will be increasing for us. Implies that K depends upon the temperature as well as catalyst we have. Rate is independent of initial concentration or pressure. Since we are defining K per unit concentrations, definitely it is going to be independent of initial concentration or initial pressure we have. And it indicates what? Larger the value of K indicates that rate is going to be higher, means faster the rate of reaction. So higher the value of K means higher the rate of reaction we can say. This is regarding the rate constant or velocity constant or as specific reaction rate. Then comes to the molecularity of a reaction. Now when you take an elementary reaction means a reaction which happens only in one single step, that is called elementary reaction. So in the elementary reaction, the molecularity is total number of reactant molecules present in the balanced equation. For an elementary reaction means happening only in one single step. In such elementary reaction, molecularity means total number of reactant molecules present in the balanced chemical equation itself is called molecularity of a reaction. When it comes to a complex reaction means reaction taking place in more than one step is called a complex reaction. In the case of complex reaction, each and every single step has its own molecularity. In the case of a complex reaction, there are multi-steps in that. So each and every step has its own molecularity in the case of complex reaction. And it is given by the mechanism of the reaction. Molecularity comes from the mechanism of reaction, and molecularity cannot be fraction or zero, and it is always a whole number. Cannot be a fraction or zero, and the value cannot be more than 3. Implies that we have 1 or 2 is the molecularity of any reactions we have, because it's not more than 3. Rarely we have 3. So 1, 2 and 3 are the possible molecularity of reactions. Always a whole number, cannot be a fraction value, cannot be 0, comes from mechanism, means it is nothing but a theoretical concept we have. This is regarding the molecularity of a reaction. Then comes order of a reaction. The sum of the powers to which the concentration terms are raised in the rate law itself is called order of a reaction. Sum of the powers to which the concentration terms are raised in the rate law itself is called order of reaction. It is always an experimentally determined quantity. Doesn't come from a theoretical concept. It's only experimentally determined quantity we have. Suppose we have a reaction like this: A moles of A plus B moles of B, giving rise to, say, products now. Now rate law will be given as rate constant K into A to the power of X into B to the power of Y here now. A power X and B power Y we have. The terms X and Y, that is the powers in the rate equation X and Y, need not be the coefficients of A in the balanced equation. Because these powers X and Y are in the rate law are determined from the experiment. They are given by the experiment here now. Whereas A and B in the equation are obtained by balancing the equation. So here powers X and Y are coming from the experimental data, whereas A and B are obtained by balancing the chemical equation. So these two may or may not be same. So therefore, the sum of the powers means, now in this case here, X plus Y itself is called order of reaction. So sum of the powers to which the concentration terms are raised in the rate law itself is called order of a reaction, and X and Y are experimentally determined quantity, and they are not coming from the balanced equation. This is regarding order of reaction. Let us take for a reaction A giving rise to products P now. Say time t is equal to 0. Let us take A is a concentration of reactant A. At time t is equal to T, suppose X moles are reacting. Implies we are left with only A minus X after a time t we have. Implies X is the amount reacting for us now. X moles are reacting here, and we are left with A minus X we have. Now the rate of reaction. Rate is always given by change in the concentration per unit time. So starting with A, we have now A minus X means X moles are changing now. So X moles are reacting. So rate is given by dx by dt, amount of change, which is also given by rate constant K into A minus X whole to the power of N we have. Now here this is nothing but, this is called differential equation. Dx by dt is nothing but rate of reaction. K into A minus X to the power of N. X is the amount reacting in a time t we have. N stands for the order of reaction, which itself is called differential equation. Now, if you are integrating the differential equation here, we are going to get different equations, that is, we are going to get different integrated forms we are going to get now from this. So, for example, if you take in this case, say if at all N is equal to 0, say for 0 order reaction, then rate will become equal to K into everything becomes 1 only, because anything power 0 became 1. So rate became equal to rate constant K. That implies that rate of reaction is completely independent of the concentration of reacting substances in the case of 0 order reaction we have. So in the case of 0 order reaction. So when you are integrating the differential form, we are going to get the integrated forms of the various equations. Those things can be derived. And finally, you are going to get a table of this form. So here we have integrated rate equations for different reaction orders. So 0 order reaction, K is equal to A minus x by T, or simply we can write K is equal to x by T also in this case, is also equal to x by T here now. Coming towards units of the rate constant K, we can take general form as units of rate constant K is equal to, it will be molar seconds inverse, that is moles per second per moles per liter per second by molar to the power of say n here, where n is the order of reaction. When you take a 0 order reaction here, n is equal to 0 here now. N is equal to 0, this becomes 1. So units will be molar seconds inverse or else mole per liter per second we have. And coming towards half-life period, by substituting A minus x as A by 2 half, you are going to do the expression A by 2k. So for 0 order kinetics, rate constant K is equal to x by T and half-life is equal to A by 2k we have. Implies half-life is proportional to initial concentration. Then first order kinetics, K is equal to 2.303 by T into log of A by A minus x here. And units are seconds inverse. Substitute here, say in this expression, n is equal to 1 now. So therefore m and m gets cancelled. We are left only with the seconds inverse. So here is seconds inverse we have. And half-life is given by 0.693 by K. Second order reaction, K is equal to x by AT into A minus x we have. And again substitute here value 2 in this case now. You are going to get this expression liter per mole per second, and half-life is given by 1 by K. So these formulas we need to remember while solving the problems. That is a 0 order reaction, K is equal to x by T. 0 order reaction, half-life is A by 2k we have. First order reaction, K is equal to 2.303 by T into log of A by A minus x, half-life is 0.693 by K. Second order reaction, K is equal to x by AT into A minus x, and then 1 by Ka is a half-life of second order reaction. So these formulas should be remembered while solving the problems. Then when you go to the fractional order reactions here, fractional order reaction, the rate of reaction is dependent on the fractional power of the reactants we have. In the case of fractional order reactions here, the rate of reaction depends on the fractional power of the reactants. So for example, H2 and Br2 giving rise to 2HBr, rate is equal to, rate law is given as H2 to the power of 1 and then Br to the power of half we have. Sum of these two powers is 3 by 2. So for this reaction we say that order of reaction is equal to 3 by 2 because sum is equal to 1 and then half we have. Similarly, other reactions, CO plus Cl2 giving rise to COCl2. The total order is being found to be 5 by 2 here. And CHO, CH3CHO, acetaldehyde giving rise to CH4 and CO, it is being found to be 3 by 2. These three are the examples given to us as the fractional order reactions. So the examples we need to remember, because which are the following having fractional orders, they may ask in that way also. So H2 plus Br2, CO plus Cl2, acetaldehyde giving rise to. These are the examples for the fractional order reactions. Then comes the pseudo-order reactions we have now. Pseudo-order reactions here, the reactions, first of all, meaning of this one, pseudo-order reactions whose actual order is different from expected order from rate law itself is called pseudo-order reactions we have. Pseudo-order reactions means the reactions whose actual order is different from that expected from the rate law itself is called pseudo-order reactions. So for example, they can take first order reactions whose molecularity is 2 or there more than 2 we have. Suppose when you take a reaction like hydrolysis of ester or inversion of sugar, let us see the reaction like this. Say ester or COOR dash plus water giving rise to acid plus alcohol we have. Now for this, the expected rate law, the expected one. The expected rate law is equal to rate constant K into concentration of R COOR into that of H2O we have. Since water is taken in large excess, the rate will be independent. The rate will be independent of the concentration of this. So therefore now the actual rate law, that is rate is given by K dash into concentration of ester we have. Concentration of ester. Here K dash will be equal to K into concentration of H2O. So this will be another constant because you are taking excess of the water, the concentration. It will be 55.5 molar. So this always remains constant. Now this is said to be a pseudo first order reaction. Actually order appears to be 2. Order appears to be 2 because of these two components that are involving the reaction. Appears to be 2, but actually order is 1. Such type of reactions are said to be pseudo order reactions. So pseudo order reactions means reactions whose actual order is different from that expected from rate law itself is called pseudo order reactions here. The next how to find out the order of reaction, various methods we have. First one is a graphical method, applicable only if you have one reactant. The integrated rate equation expression of the various orders are converted into y is equal to mx plus c form, means straight line form, and a graph of a function of concentration against the time is drawn. The order of the reaction corresponds to the expression which gives the straight line. So here what we are doing is we are converting the integrated rate constant expressions into the y is equal to mx plus c form, and then we are plotting a graph between the concentration versus time t. If you get a straight line that corresponds to that particular order of reaction. For example, if you take a zero order reaction, rate constant K is given as A minus x by T. Zero order now. Let us bring this into the y is equal to mx plus c form. Y is equal to mx plus c form. So that is to say Kt is equal to A minus x here. Bring this to other side now. So A minus x is equal to minus Kt plus A we have. We take this as y-axis is equal to mx plus c now. Implies when you plot the graph here, on this axis is y minus x here now. It is time t in this case. We get a graph of this type here, and slope of this graph is equal to minus k. So when you are plotting a graph for log a minus x and time t, if you get a straight line having a negative slope, then that can be said to be a zero order reaction. In this way, we are going to change the integrated expressions into form y is equal to mx plus c, and we are going to plot the graphs. This is an example taken for this zero order reaction example we have. Similarly, for all we can derive the expressions. So a minus x versus t, straight line stands for a zero order reaction. If you plot log a minus x versus t, a straight line, then that is said to be a first order reaction. If 1 by a minus x versus t, straight line, that is said to be a second order reaction. All these things are obtained from the rate expressions which are given in the table previously. So take the equation, bring in the form of y is equal to mx plus c, you are going to get straight lines in these cases now. This is regarding determination of order of reaction, which is called graphical method. Next one, Ostwald's isolation method we have. In Ostwald's isolation is applicable for 2 or more than 2. So graphical method applicable only for one component system. It is applicable for 2 or else more than 2 components we have. This method involves the isolation of one of the reactant by taking all other reactants in large excess. So here principle is, if you take a component in excess, the rate is going to be independent of the component which you are taking large excess quantity. Suppose you have 2 components, say A plus B, giving rise to product P we have now. Now if you take A in excess, suppose if A is in excess, then rate will be independent of A. And then we can find order with respect to B, we can find out. So we are taking A in excess, then the rate will be independent of A. So now we can find out the order of reaction with respect to B. In second case, we can take B in excess, then rate will be independent of B, then you can find out order with respect to A. Then you can add those two orders. So in this method involves isolation of one of the reactant by taking all other reactants in large excess, because rate will be independent of the reactant which we take in excess quantity. So you can find out in that way. Let us take here. So the order with respect to the reactant is determined, means that which you are taking limited amount. The process is repeated for all other reactants. Finally, sum of the powers of all the reactants gives us the order of the reaction. So we isolate one among them. This is regarding isolation process. Then comes half-life method we have. This is said to be half-life method. Half-life method. So in this method, half-life proportional to 1 by a power n minus 1, where n is the order of reaction here. A stands for the initial concentration there now. So n is the order, A is initial concentration. So we'll be changing the initial concentration, we'll be finding out the half-life of that reaction. And then we are going to get order by this formula. N is the order of reaction given by 1 plus log T2 minus log T1 by log A1 minus log A2. Here T2 is a half-life when initial concentration is A2 we have, and T1 is a half-life when you have initial concentration as A1 we have now. So N is equal to 1 plus log T2 minus log T1 by log A1 minus log A2 we have. Where here the principle used is half-life is proportional to 1 by a power n minus 1. In that way, this can be used to find out the order of reaction. Then, the effect of temperature on the rate of reaction. It is experimentally found that for every 10 degrees rise in temperature, the rate of reaction doubles to triples. Means it varies from 2 times to 3 times we have. For every 10 degrees rise in temperature, rate of reaction almost doubles to triples. Means varies from 2 to 3 times now. The ratio of rate constant of reaction at a particular temperature to the rate constant of the reaction at a temperature 10 degrees below is called temperature coefficient. At a particular temperature and then 10 degrees below, the rate constant's ratio itself is called temperature coefficient we have. So we suppose you have taken at 30 degrees Celsius, 30 degrees Celsius rate constant. Now we can take temperature coefficient as it should be K30 by K20 itself is called temperature coefficient of the reaction. Now difference must be 10 degrees. This will be 10 degrees lower, this will be 10 degrees higher we have. So mathematically you can write here K, it is T plus 10 by KT we have. It should be nearly equivalent to 2 to 3 times we have. And it's called temperature coefficient of the reaction. Then the relation between the T and then K is given by Arrhenius equation. Given by the Arrhenius equation, where the K is given by A into e to the power of minus EA by RT. E to the power of minus EA by RT. And if you take logarithmic forms, finally you are going to get log K is equal to minus EA by 2.303 into 1 by T plus log of A we have. When you plot a graph for this, so the graph means here you are taking log K here and 1 by T means Y here M X plus C we have. So we have taken X axis as a 1 by T value there now. Y axis we have taken log K now. So we are going to get a straight line having negative slope because negative value is there now. Slope is going to be negative for us now. So for this value, slope is equal to minus, it is EA by 2.303 into R we have. That is the slope now. So Arrhenius equation gives the relation between the rate constant K and the temperature of the reaction. So these are the two forms to remember. That is a exponential form as well as the logarithmic forms. And graph we are plotting with a log K and 1 by T. We are getting a slope, negative slope, and slope value is equal to minus EA by 2.303 into R we have. Then in two different temperatures, if you take the same expression, we are going to get like this: log K2 by K1 is equal to EA by 2.303 into R T2 minus T1 by T1 T2 we have, where K2 is the rate constant at a temperature T2 we have, and K1 is the rate constant at temperature T1 we have. Regarding log K2 by K1 is equal to EA by 2.303 into T2 minus T1 by T1 T2 regarding Arrhenius expression. Then comes catalytic influence on the rate of reaction. The presence of a positive catalyst alters the reaction path in such a way that it will be decreasing the energy of activation. Thereby, rate will be increasing for us now. A positive catalyst will be decreasing the energy of activation and increases the rate of reaction. If you take a negative catalyst, this also alters the rate of reaction by changing the path of a reaction now. That is, in such a way that it will be increasing the energy of activation and thereby decreasing the rate of reaction. So, catalyst is always altering the path. So, a positive catalyst alters the path, means it alters such a way that it is decreasing the energy of activation and increasing the rate of reaction. Negative catalyst means this also alters the path such a way that it is increasing the energy of activation and decreases the rate of reaction. Then comes the collision theory of reaction rates we have. According to this theory, the collision theory of reaction rates, a chemical reaction takes place due to a collision between the reactant molecules. Means without collision, a reaction cannot happen according to collision theory of reaction rates. And for these collisions to be effective in nature, there are two things. Reactant molecules must possess required energy to react, and then reactant molecules must have proper orientation. So, unless collisions are taking place, reactions cannot happen. There is one point here. Then the collisions must have required amount of energy. Third point is that they must have proper orientation. Then the reaction will be fruitful. Now let us take meaning of the energy terms involved in the collision theory of reaction rates. The minimum energy that reactant molecules must possess in order to form products is called threshold energy. The minimum energy that reactant molecules must possess in order to form products is called threshold energy. And the excess amount of energy required by reactant molecules so as to attain threshold energy is called activation energy. The excess amount of energy required by the reactant molecules so as to attain threshold energy is called energy of activation. Energy of activation can be given as ET, threshold energy, minus average energy of reactant molecules. So EA is given by ET minus average energy of reactant molecules. Let us see a graphical representation for this. That is to say, when you take on this axis energy on this axis, and say path of reaction on this axis. Now let us suppose this energy of reactant molecules. Let us put it as ER, energy of reactant molecules. So they must attain energy so as they react, means the graph goes like this. So this value can be taken as ET, means threshold energy. The energy is from here to here. It's called threshold energy now. Then here the reaction takes place and products are being formed. And may suppose the graph is coming like this. Now this value can be taken as energy of production now. So right from here to here, this is called ET. This is called threshold energy. And then this is called average energy of reactant molecules. This part is called average energy of reactant molecules. Now difference between the energy of reactant molecules and threshold energy, this value, this gap, this is called energy of activation. This is called EA for us. So EA will be equal to ET minus energy of reactants. And this is the energy of products we have. This difference can be taken as delta H also. Means energy of products minus energy of reactants we have. So if it is say backward reaction, then these are the reactants, these are the products will come. So this is the energy diagram we have. To understand energy of activation, threshold energy, energy of reactants, energy of the products, and delta H of the reaction we have. Then, so according to molecular collision theory, the rate is given by Pz in e to the power of minus Ea by Rt. So P is called orientation factor, because the theory says that it depends upon the molecules which are properly oriented also. So orientation factor means the fraction of the molecules properly oriented for effective collisions. So there must be collisions, they must be properly oriented, they must have energy also now. So P stands for orientation factor. Z is the collision frequency we have, means number of collisions made by the molecules per unit time, collision frequency. And e to the power of minus Ea by Rt is also known as Boltzmann factor, is known as Boltzmann factor, and is a fraction of molecules having energy equal to or more than E. That is a fraction of activated molecules, So there are three things in collision theory. So P orientation factor, Z collision frequency, e to the power of minus Ea by Rt, the fraction of molecules having energy equal to or more than that of E, that is nothing but fraction of activated molecules we have. So then the reaction takes place. Now coming towards for an endothermic reaction and exothermic reaction now. So for endothermic reaction, the same graph you can take like this. For endothermic reaction, the energy of products will be more, thereby the graph comes like this. The endothermic reaction here now. So endothermic reaction is the energy of reactants, energy of the products we have. And here threshold energy. And this will be energy of activation now. And say if it is a reversible reaction, then from here to here the reaction takes place now. Thereby this part means from here to here now. This will be taken as energy of activation, but for backward reaction. Let us put EAB here now. This will be EAF then now. So in the case of endothermic reaction, energy of activation of forward reaction, take from here to here, forward reaction, from here to here, this point, is greater than energy of activation for backward reaction. This part is called for backward reaction energy of activation now. And if it is say for exothermic reaction, it is going to be reversed then now. For exothermic reaction, it comes the other way. That is to say, this will be exothermic graph we have. So energy of activation for backward reaction comes from here to here then now. This is called energy of activation from here to here. EA backward reaction, forward reaction we have. Difference, this is more than that. So delta H value can be taken like this. Energy of activation for forward reaction. So EAF minus, you can take EAB as a formula to find out delta H value. EAF minus EAB also gives the difference of delta H values. Then comes radioactivity. Since radioactivity follows first order kinetics, radioactivity problems can be solved using first order relations only. So formulas will be remaining same as that of the first order relations because radioactivity follows first order kinetics. Today we will discuss important points from solid state chemistry. First of all, meaning of solid substance. Substances having definite size and shape are called solids, and solids are classified into two different categories. First one is crystalline solid, other one is called amorphous solid. When it comes to crystalline solid, they have regular arrangement of particles. Due to this, they have definite geometry. When it comes to amorphous solids, they do not have regular arrangement of particles. Therefore, they do not have regular geometry or shape. And the properties are said to be anisotropic in the case of crystalline solids. That is because they have physical properties such as refractive index, conductivity, different in different directions. Therefore, the properties are anisotropic. When it comes to amorphous solids, their properties are said to be isotropic because they have various physical properties same in all directions. They have same in all directions. They have different values in different directions in the case of crystalline solids. Hence they are called anisotropic. So isotropic stands for same properties in all directions. They have sharp melting point, and here they do not have sharp melting point. And coming towards, in the case of amorphous solids, when you are heating it, they first of all soften and start flowing down. In the case of amorphous solids, there is no sharp melting point. They have definite heat of fusion. In crystalline solids, they do not have definite heat of fusion in the case of amorphous solids. When you take examples of crystalline solids, we can say sodium chloride, then potassium chloride, graphite. These are the examples of some of the examples of crystalline solids we have. Amorphous solids, we can take rubber, plastic, and say glass. They are said to be amorphous solids. Let us take now different types of crystalline solids. Types of crystalline solids. Crystalline solids may contain atoms, ions, or molecules at the lattice points. They may have atoms, ions, or molecules at the lattice point. Depending on the nature of these particles, there are 4 types of crystalline solids. Depending on the nature of the particles present at lattice points, there are 4 types of crystalline solids. First of all, ionic crystals. Now, ionic crystals contain cations and anions at their lattice points. So, for example, rock salt, that is NaCl. So, NaCl contains Na plus and Cl minus ions at the lattice points of the crystal. So, ionic crystal contain cations, anions at the lattice points. Covalent crystals. The covalent crystals contain covalently bonded atoms at the lattice points. So, for example, diamond. So, covalent crystals contain covalently bonded atoms at their lattice points. Coming towards molecular solids or molecular crystals, the molecular crystals contain molecules of chemical substances at the lattice points. They have molecules of chemical substances at the lattice points. These molecules are held either by van der Waals forces or dipole interactions or even by hydrogen bonding. Now, so these molecules are held by van der Waals forces or dipole interactions or hydrogen bonds. So, for example, dry ice, that is solid carbon dioxide, and solid ammonia are the examples of molecular crystals. So, molecular crystals contain molecules at the lattice points of the crystal. Then comes metallic crystal. Metallic crystal contains metal ions at the lattice points submerged in a sea of electrons. So, metallic crystals contain metal ions in the lattice points submerged in the sea of electrons. And metallic bond strength depends upon the number of electrons involving in the metallic bond. Metallic bond strength depends on number of electrons involving in the metallic bond. So, metals such as copper, zinc, silver, etc. have metallic crystals. Then comes meaning of space lattice, unit cell, and then lattice points. Space lattice, unit cell, and lattice point. Space lattice means a regular arrangement of lattice points in 3 dimensions. So when you take this one, we have a regular arrangement of points are there in 3 dimensions now. The entire thing can be called as space lattice now. This is called space lattice. So space lattice contains a regular arrangement of lattice points in say 3-dimensional space. It's called space lattice. And the point in a space lattice, here, space lattice, which represents the constituent particle which may be atom, molecular ion, is called lattice point. So these are the lattice points which are actually representing the atom or ion in the space lattice now. And coming towards the meaning of unit cell, the smallest portion of entire space lattice, which when repeated in 3 dimensions generates the complete space lattice itself is called unit cell. The smallest portion itself is called unit cell, which actually gives the properties of the entire space lattice. So space lattice, unit cell, lattice points. So lattice points means the points which are actually representing atoms or ions or molecules in the space lattice. And the unit cell means the smallest portion which when repeated three-dimensionally generates the entire space lattice. These are the definitions of space lattice, unit cell and lattice points. Then the same thing repeated once again, the lattice, crystal lattice. Crystal lattice or space lattice is defined as regular pattern of lattice points which indicate three-dimensional arrangement of atoms, ions or molecules. Then lattice points. A point in a crystal lattice which represents the constituent particle which may be atom or molecule or ion is called lattice point. And the smallest portion or space lattice which when repeated in three dimensions generates the entire crystal, and it represents the properties of the space lattice. Unit cell represents the properties of the space lattice. This is regarding the basic fundamental definitions. Co-ordination number. Co-ordination number is number of nearest neighboring particles present in crystal. Number of nearest neighboring particles present in a crystal itself is called co-ordination number. Let us take the previous structure once. If you take the middle one here, it is surrounded by altogether 1, 2, 3, 4, 5 and 6 now. It is surrounded by altogether 6 are there here. That is 1, this is 1 here, 2, 3, 4, 5 and 6. Therefore, in a simple cube, the coordination number will be 6. Now, similarly, the coordination number in body-centered cube will be 8 and in FCC will be 12. These are the coordination numbers. One has to remember. Simple cube, it is 6. Body-centered cube, 8. Face-centered cube, 12 we have. Next, types of cubic lattices. Simple cube has altogether 8 lattice points at 8 corners. So in the 8 corners we have, these are called lattice points. Altogether 8 lattice points are there in simple cube. When it comes to body-centered cube, total number of lattice points are 9 in number. So along with the corners we have 1 at the body-centered. So total number of lattice points are 9 in this case. Then comes in face-centered cube here. In face-centered cube, 8 at the corners and 6 at the face centers we have. There are the face centers. Total number comes to 14 lattice points in the face-centered cubic structure. These are the number of lattice points. Then comes how to calculate number of particles per each unit cell. Calculation of number of particles per each unit cell. Atom in the corner is shared by 8 unit cells now. Therefore, its contribution will be, contribution will be 1/8 towards the unit cell. So atom in the corner is shared by 8 unit cells. Therefore, contribution will be 1/8 now. Atom in the face is shared by 2 unit cells. Therefore, the contribution comes to only half towards the unit cell then now. And the edge is shared by 4 unit cells. Therefore, contribution will be 1/4 in the case of edge atom. Finally, atom at the center is shared by only 1 unit cell. So, the contribution comes out to be 1. So, using the contributions here, we can now calculate number of particles per each unit cell. Now, let us see the calculation part. Unit cell, we have taken simple cube. Simple cube contains only atoms in the corner. So, 8 corners into 1/8 we have. There are no atoms in the face or its center. Totally it comes to be 1. So, simple cube contains only 1 atom altogether. In face centers, we have atoms at the corner as well as face also. 8 corners, 1/8, 6 faces, 1/2. Totally value comes to 4 then now. Body centered one, we have atoms at the corner as well as the center of the cube. So therefore 8 corners, 1/8, no face center atom here. And body center 1 we have, atom comes to altogether 2. End centers, again corners and 2 opposite faces we have, the value comes out to be 2. So in this way we can calculate number of atoms per unit cell. So one has to know the contribution made by each particle towards the unit cell. Then, now the relation between the edge length and the radius of the atom in a given unit cell. When you take a simple cube, if you take only one face of the cube here, atoms will be present along the edge. So this is edge here. This will be radius r and then r. Implies edge length will be equal to 2r in the case of simple cube. In the case of simple cube, edge length will be equal to a, which is equal to 2r. When it comes to face-centered cubic structure, here along the face diagonal, atoms will be touching each other. So one atom here, one more here, one more here now. So therefore here 4r, this is r here, this is 2r, another r we have. So the a root 2 is a face diagonal, a root 2 will be equal to 4r in the case of FCC structure. That way we can find out even for BCC also. Their body diagonal, along body diagonal, atoms touch each other. Therefore a root 3 will be equal to 4r now. So simple cube, a is equal to 2r, face centered cube, a root 2 is equal to 4r, and body centered cube, atoms are touching along body diagonal, and body diagonal is equal to a root 3, and a root 3 is equal to 4r in the case of body centered cube. Then packing efficiency. Packing efficiency is defined as the ratio of volume of the spheres in the unit cell to the volume of the unit cell. Ratio of the volume of the spheres in unit cell to volume of the unit cell. So volume of all atoms in the unit cell by volume of the unit cell. So for example, when you take simple cube, if you take say simple cube now, simple cube has only one atom. Simple cube has one atom altogether. Therefore its packing efficiency will be equal to volume of that atom by volume of unit cell. Volume of unit cell we have. So therefore you should find number of atoms of the unit cell and find out the volume of all the atoms of the unit cell divided by the volume of the unit cell. So on calculations we are going to get packing efficiency for simple cube as 0.52, means it is 52% we have, and FCC 0.74, that is a 74% occupancy we have, and BCC we have 68%. So this can be done on calculations. So packing efficiency of simple cube 0.52, FCC 0.74, BCC 0.68 we have. Then next formula is the density of the unit cell. Density is given by mass of the atoms of unit cell by volume of the unit cell. Fundamental formula, as already know, density is equal to mass by volume. It is now mass of the atoms of the unit cell by volume of the unit cell. And formula it comes to be Z into M by A cube into N. Here Z stands for number of atoms per unit cell. Suppose it is a simple cube, value will be equal to Z is equal to 1 for simple cube, and body centered cube value is equal to 2, and FCC the value is equal to 4. That way the value of Z comes. M is the molar mass of the atoms which are present here. A stands for edge length and N is the Avogadro's number, the constant value. So density is given by Z into M by A cube into N. Then comes close packing in 3 dimensions now. There are 2 different types of packing we come across. AB type. So AB type is also known as HCP structure. Total number of lattice points are 17, means if you count all the points here, say 1, 2, 3, 4, 5, 6, 7, that way we count all of them, the value comes to 17 lattice points are present there now. Now the number of atoms per unit cell is equal to 6 in this case, because here the corner of atom is shared by 1/6 here, corner is shared by 1/6, and the middle one, face one shared by, means contribution is half we have, and the center one contribution is equal to 1 we have. Basing upon all these things means 1/6 into 12, and then half into 2, and 1 into 3 we have. Total number comes to altogether 6. So number of atoms per unit cell are 6 now. And coordination number is equal to 12. Suppose when you consider this atom here, around this we have 6, 1, 2, 3, 4, 5, 6. Above this we have 3, 1, 2, 3. Similarly below also we are going to get 3 if we continue the structure. means therefore 6 in that plane and 3 above and 3 below we have. Total number is equal to 12 we have. So HCP structure, total coordination number is equal to 12 and packing efficiency is 74. So AB type is called HCP, lattice points 17, number of atoms 6, coordination number 12 and 75% is the packing efficiency we have. The next one is said to be ABC type we have, and it is also known as FCCRL CCP structure, cubic closed packing or face centered cubic structure we have. Number of lattice points are 14. Already we have seen the number of lattice points in FCC structure in the previous table. Now number of atoms per unit cell also we have seen as 4. Coordination number is 12 and same as that of we have packing efficiency same as that of AB type here. The coordination number 12 you can understand here. If you consider say this atom here in this one, in the plane, along with the plane there are 6 atoms here and 3 are here and 3 are here. Therefore this atom is surrounded by altogether 12. So coordination number is once again 12 in this case. Both have same coordination numbers. So therefore both have same packing efficiencies also. AB type of crystal structure you have. Then comes what are the properties of the cubic cells now. It's actually a summary of all the previous things which you have seen till now. Simple cube, 8 lattice points, number of atoms are 1, coordination number 6 and A is equal to 2R we have seen packing efficiency as 0.52. Body centered cube, lattice points that is 9 we have, means 8 plus 1, 8 corner, 1 in the body center, number of atoms are 2 altogether, coordination number 8 and A root 3 is equal to 4R because along body diagonal atoms are touching each other and 0.68 here. And FCC structure, lattice points are 14 here, number of atoms are 4, coordination number is 12 here, and here atoms touch along the face diagonal, therefore A root 3 is equal to 4R and packing efficiency is equal to 0.74 we have. Then comes different types of voids we have. 2 types of voids we come across here, tetrahedral void and octahedral void. Tetrahedral void is the vacant space formed by 4 spheres. Itself is called tetrahedral void, and number of tetrahedral voids will be equal to twice the number of atoms or spheres in the crystal. Octahedral void means the vacant space formed by 6 spheres is called octahedral void. Number of octahedral voids is equal to number of atoms in the crystal. Now when you take the ratio of the atoms to voids, say ratio of atoms, say to voids, atoms to voids, the ratio will be say 1:2 we have. Means here number of atoms, so 1 we have. Then this 1 will be octahedral void. The 2 will be tetrahedral voids we have now. So 1 atom will have 1 octahedral void and we have there 2 tetrahedral voids. So the ratio of the atoms to voids in all crystalline structures if they are close packed. There are 2 tables to remember in solid state chemistry. One is a limiting radius ratio table because the limiting radius ratio gives rise to coordination number and structure. And the meaning of limiting radius ratio is nothing but the ratio of the radius of cation to that of radius of anion. This ratio itself gives rise to the coordination number and the structure. If the radius ratio is between say 0.155 to 0.225, coordination number will be 3. It comes under triangular planar structure. If it is between 0.225 to 0.414, coordination number is 4. Structure will be tetrahedral structure. If it is between 0.414 to 0.732, coordination number is 6, comes out to octahedral structure. And if it is 0.732 to 1, coordination number is 8, comes out to be cubic structure. So we need to remember the ratios, coordination numbers followed by the respective structures we have. Then comes one more table to remember, that is to say Bravais lattice structures now. Now the Bravais lattice structures, there are 7 basic crystal systems which can be categorized into 14 crystal systems we have, and they are called Bravais lattices. Let us take the dimensions of these Bravais lattices. The cubic one, all 3 will be equal, axial distances, A is equal to B is equal to C we have. In cubic structure, all angles are also equal. Alpha is equal to beta is equal to gamma, and each angle is equal to 90 degrees we have now. Tetragonal structure, one of the lengths will be different, means A is equal to B, not equal to C we have, but again all angles will be equal to 90 degrees we have in the case of tetragonal also now. Then comes orthorhombic form here. All lengths will be unequal, we can say, means no length is equal to other one now, but again here also all angles will be equal to each other and also equal to 90 degrees we have. And there are here in this one we have simple, body centered, face centered, end centered we have. So 4 structures are there in this structure. Then comes rhombohedral form. Once again all lengths are equal in this case, but angles are also equal, but no angle is equal to 90 degrees we have in this structure. So all are equal, all our angles are also equal, but no angle is equal to 90 degrees in this case now. Next comes hexagonal structure. Again one of the lengths is not equal to other one. 2 angles are equal. Alpha and beta angle will be 90 degrees here, but gamma will be 120 we have. We have only one structure, a simple structure we have. Then comes monoclinic and triclinic structures we have. Monoclinic and triclinic, in all the structures here, no side is equal in any of these 2 cases now. All sides are different. When it comes to monoclinic here, 2 angles are same. Say alpha is equal to gamma is equal to 90 we have, but here beta is not equal to 90 in this case now. When it comes to triclinic structure, alpha not equal to beta, not equal to gamma here, and also not equal to 90 degrees we have now. So in completely, if we see the summary of all the structures here, most symmetric form is cubic form, because all lengths are equal, all angles are also equal, and each is equal to 90 degrees we have. And highly unsymmetric structure is triclinic structure. No side is equal, no angle is also equal in this case, and not equal to even 90 degrees for us now. With this we are done with Bravais lattices. Then comes defects in crystal structures. So stoichiometric defects. The point defect which do not disturb the stoichiometry of solid itself is called stoichiometric defect we have. And there are 2 types here. Schottky defect. This defect is caused when equal number of cations, anions are missing from the lattice, from the crystal lattice. Density of the crystal will be decreasing because number of ions are being lost. So ions are being lost means mass will be getting reduced, but volume of the crystal will not change, and therefore density gets reduced in this one. And these are normally shown by high coordination number compounds like NaCl, KCl, CaCl will have Schottky type of defect where a pair of ions will be missing and density also gets reduced. Next is Frenkel type of defect here. This defect is caused when an anion, when an ion, normally it will be cation because of smaller size, when an ion is missing from its lattice point but present in the interstices of the crystal. It is present somewhere in the structure but not in its point. That type is said to be Frenkel defect here. Density will not change because the atom is present, not missing altogether now. It is shown by low coordination number compounds like zinc sulfide, silver chloride, silver bromide, silver iodide we have. But we need to remember one point here, AGBR shows both the defects, both the Frenkel as well as Schottky type of defects.